So it's a new type of motion. It's not circular motion, right? It's an up and down motion. It's a vertical rectilinear motion. Okay? So this is, think about a mass is attached to a spring. So this is equilibrium position. After 10 hours, the solution in a way is summarized in the following way. This Hooke's principle is actually the shadow image of a circular motion. That's the answer. The moving up and down motion is really shadow of the circular motion with a constant angular speed. This is rotating around, circle like this, with a constant angular speed, and you have a flash, and then it's creating the shadow on the wall. That's going to exactly, perfectly model that spring mass system up and down, or guitar string, anything that follows the Hooke's principle. Mathematical solution is actually coming from this circle thing. Okay? So that's really amazing to me. What is this right triangle got to do with this spring going up and down? But here's the picture and mathematical explanation you will get eventually in differential equation course. Motion is a shadow image of this circular motion with a constant angular speed, right? So that's what we're about to we get that, and I'm going to explain the graph of sine t in here. And I'm going to stop right there. No, we'll run it. That's a perfect shot there. And I'm going to use this one to explain the graph of the sine function. Okay? This is a unit circle. There's a 1 in there, -1, -1, and 1 there. Does that make sense? It's a unit circle, and here's a terminal point with practice limit x comma y there, right? And we're looking at this, about to sketch the graph called y equals sine t. That's what we're about to do. And here is the horizontal axis, stretch it here like this, t-axis in there. And the vertical axis there, there's a y-axis there. Okay? This is where t equals 0. And this is where t equals whatever, like almost pi over 4. So this is the t value. T radian. Make sense so far? So who remembers the relationship between x and y and t on the unit circle? Sine t is y, right? Y divided by 1. Cosine t is x divided by 1, right? But we are focusing on y equals sine t there. So here, that y here is exactly the same y here, y coordinate. So whatever the t value is, the value sine of t is this y coordinate right there. This is the value of sine t. So let me use it here like this. That is the value of sine t there, represented as the length of that vertical dark bar there, right? That's the value. So what I'm about to do, rather than using a calculator, I'm showing you that how to roughly generate these values. All right? So that value is exactly translated here. So that's the y value. That's the sine t value right there. Okay? But this t radian is quite odd. T is a magnitude of angle, but you have to expand it horizontally, right? So if this is roughly, for example, pi over 4, what is pi over 4? Can somebody use a calculator to get this one from pi over 4? Is it 0.8 something? 0.78, something like this. So you go from t equals 0, here 0.78 some unit there. That's the length here. So t was originally measure of angle, but kind of expanded horizontally, like a time. Horizontal axis here is the time. After 0.8 seconds later, let's represent this angle is kind of horizontal, put it there. That sine value there, what is the sine of 0.78? That value is the same as that vertical length. Slide it here. Okay? So 7.78, you get this number from a calculator, and you actually sketch it, is really like this one is slided towards there. Okay? So, again, the y-coordinate of this is exactly the sine value. The y-coordinate is well represented here. This guy going up and down, right? And the graph of this one is that you're not just going up and down and here, expanded with the time. So you're going to the right while you're going up and down. And that's what this movie is about, right? So focus in here. These are the y-coordinate. This is exactly the y-coordinate that is well represented here. So you're going up and down. That's the y value. But at the same time, you move to the right. In this graph here, representing the time is passing, right? So these are the time, these are the magnitude of the angle or the time, and the sine value is exactly the location of this one, y value in there. So this is a graph of a sine if you sketch it. Horizontal axis is a magnitude of the angle or time t or just the real numbers. So how are you going to remember this one? Sine starts at this part, the 0, right? The sine value is going up and down and up and down and expanded over time. So started here, not just going up like this, and follow at the same time going to the right and the left. Like this. So I'm going to hide this one. I'm going to ask you to actually sketch it one more time. And I'm just going to discuss one more important thing, then I'll let you guys go. So I want you to practice here. Here's a t-axis, and here's a y-axis. Think about, you start from here in the equilibrium position. Actual motion is going up and down, right? So think about not drawing it, hovering over the paper, just move the pen up and down like this, right? That's the actual motion, but you're actually doing that at the same time going to the right. So see if you can generate that sine curve graph function by yourself. I hope you got this picture, right? You start at the 0, go up and down, and come back to the original position, right? Right, that's the rough shape. So what additional thing we're going to do is a little bit of more information than just rough sketch in here. So this is where t equals 0, right? What do we know about this point in here? Something simple, right out of the graph. Is y-coordinate 0, right? At the beginning, like time equals 0, y-coordinate was 0. Does that make sense? We start at the equilibrium position. And it says a few seconds later, it came back to the y equals 0 again, right? So here is the initial position right there. I'm going to use the red one. Initial position is moving around. When is it coming back to the y equals 0 again? First time. Right over here, right? Isn't that where y equals 0? Y equals 0 is 0. But what is the t value there? T value is not -1. T is the angle. Remember? Yeah, t is this angle, 180. But in radian, what is it? Pi. After pi seconds later, its location is going to be 0 again. That's what this means right there. So t equals pi there, right? So it says here y equals 0 again. You agree? When is y equals? This is where y equals 0. What is the next moment y equals 0? Over here is a 2 pi. So you know t equals 2 pi, right? Good. So this is another interesting point. It's the highest y-coordinate. Isn't that right? The highest y-coordinate? So I want you to start from the initial again. Doing the circular motion, where is the highest y-coordinate appearing first time? At the North Pole, right? The North Pole here. That's where it's appearing. What is the y-coordinate there? 1 is a unit circle, is 1. When is it happening? What is the t value there? It's this angle, exactly pi over 2, right? So at pi over 2, that highest coordinate 1 is obtained, right? All right, there's another point that's interesting. It's the lowest coordinate, right? What is the lowest coordinate? If you look at the circle, where is the lowest y-coordinate? -1, down there, right? So when is it reached? And although in the first quadrant, the second quadrant, it never reached there. Finally, it reaches here for the first time, the lowest coordinate, right? What is the angle there? 3 pi over 2. Pi over 2, pi over 2, and pi over 2, right? So that is obtained in t value what? 3 pi over 2. So when you sketch the sine graph, your calculus instructor will assume that you know these numbers. 0 and pi over 2 and pi and 3 pi over 2 and 2 pi and 1 up there, -1 down there, right? That's it for today. We'll continue with these graphs and model some of this harmonic motion later on.